Let's begin by defining a wheel. A wheel is any cycle graph that also contains a central vertex called a hub, such that every vertex in the cycle is connected by a single edge to the central hub. A unicycle is a connected graph with only one cycle. In other words, a unicycle is a tree that has had one edge added to it. A spanning tree is a tree that includes all of the vertices with the fewest number of edges. A cycle that overlaps at one vertex with a spanning tree is a unicycle. In this example, we have a cycle on 3 vertices that shares one vertex with a spanning tree on 3 vertices. The cycle shares one vertex with the tree, and therefore the 5-vertex graph that results is a unicycle.
Here we have an example of a collapsed graph. In a collapsed graph, you choose a subgraph in the original graph and you condense that subgraph into one vertex. That one vertex maintains the same degree sum and same connections with each vertex. Now we will collapse the rim of the graph, which is the outside. The rim condenses into one vertex, while the remaining vertex stays as is. Because the degree of that remaining vertex is 4, we have 4 edges that connect the collapsed vertex and the remaining vertex. In a wheel, the central vertex that touches every other vertex is called the hub. A spanning unicycle is the result of the collapsed graph. The cycle of the spanning unicycle is equal to hub plus k, where k is the selected number of vertices to be collapsed, and n is the total number of vertices on the outside. K must be between 2 and n.
So I do hope you guys have remembered the idea of collapse because it is going to help us along the way. But for now, let me introduce a new idea to you which will also be helpful for along the way. This idea is called Kirchhoff's tree theorem. Basically, what it states is that in order to find the number of spanning trees in a wheel graph, the idea is that you have to compute the determinant of the Laplacian matrix of this graph. Now, this might get confusing, but you might want to ask, what is a Laplacian matrix? Basically, it is a matrix that is named after French mathematician Laplace. And what he says is that a Laplacian matrix equals to a degree matrix subtracted by an adjacency matrix. Now, what is degree matrix? Basically, taking a look at the W4 graph, you can see that the vertices are being labeled. So what you can see here is that in vertex number 1, there are 4 degrees. In vertex number 2, 3, 4, and 5, which are also called the rim vertex, the rim vertex are having the same degree of degree 3. So to denote that into a matrix, we need to find out the location of each vertex. So for vertex number 1, it is located on the first point on column 1, row 1. Now for number 2, it is located on the second point of column 2, row 2. Now for vertex number 3, it is located on column 3, row 3, third position. And the train goes onward. On that position, you want to note the degree of each vertex. So on the right side of the graph, you can see a degree matrix of a wheel 4 graph. Now knowing what degree matrix is, what is adjacency matrix? Now same thing. We label all the vertices on a wheel 4 graph. What you end up getting is that you're getting all the 1s and 0s. What it means by 1s and 0s is that A 0 means that this vertex is not connected to that vertex. 1 means that a particular vertex is connected to an adjacent vertex. So let's just take a look at row 1. Row 1 is the adjacency presentation of the connection of vertex 1. So vertex 1 is not connected to vertex 1. It's not connected to itself. We cannot see a loop here. But vertex 1 is definitely connected to vertex number 2, 3, 4, and 5. So on the second, third, fourth, and fifth position on both row 1 and column 1 are denoted a 1 because they're connected. Now let's take a look at vertex number 4. Vertex number 4 is connected to vertex number 1. It is also connected to vertex number 5. It is also connected to vertex number 3. So on the first, fifth, and the third position of the fourth column, they are denoted a 1 because they are connected. So the same thing will apply to the vertices, but for the time being, I'll just be convenient. So again, what is Laplacian matrix? It is a matrix named after French mathematician Laplace. And Laplacian matrix is degree matrix minus adjacency matrix. Now, how to do a minus in matrices is really simple. So you take the same coordination and you just minus the numbers in that coordination. So on the left-hand side, it is equal to the degree matrix minus the adjacency matrix. You can see that the 0 in degree matrix minus 1 in adjacency matrix will get you minus 1 in that same coordination in Laplacian matrix. So we know that in order to know the number of spanning trees, we have to know the determinant of a matrix. But what is the determinant of a matrix? Well, determinant is a scalar value that is computed from the elements of a square matrix and encodes certain properties of the linear transformation described by the matrix. I don't know what this means, but the simple thing I can tell you is that determinant of a matrix is a special valuation of a matrix. The result of determinant will be a number. So let's just say there a matrix A. And matrix A is a 2 by 2 matrix, A, B, C, and D. So the determinant of matrix A is equals A times D minus B times C. Now, it might seem simple to you, but when it goes to a 3 by 3 matrix, it becomes like something like this. You take out A at the top left, and then you time the determinant of rest of the bottom right. And the same thing. You pick B, you forget all the rows and columns that are involved in B, and then you compute the determinant of rest of the 2 by 2 matrix. But we also have to be careful about the plus sign and minus sign. So it'll get really wild and really complicated when it goes even further to matrices of 4 by 4, 5 by 5. But now it's just a simple idea of for you to be informed about that determinants is a valuation of a matrix, and basically how to compute determinants is not what the point of discussion is. So let's come back to Kirchhoff's tree theorem. So in Kirchhoff's tree theorem, it states that the number of spanning tree is equal to the determinant of the Laplacian matrix. Now, it's really hard to apply to, let's say, wheel graph. Can we just have a wheel, and then we turn this wheel graph into a Laplacian matrix, and then we compute the determinant of this Laplacian matrix, and then we find the number of spanning trees? Yes, we can. But the idea is that the final goal is that we are not supposed to find the number of spanning trees. Instead, we are supposed to find the number of unicycles. A unicycle is different from spanning tree in the sense that unicycles can be arranged according to the different arrangement of spanning trees. So, in fact, the number of unicycles are more than the number of spanning trees. So, because there are possibilities of where you stretch your cycle from. Okay, so why is that important? Do you still remember the collapse? Or should I say the minor transformation? So take a look at the graph below. It is basically a collapse based on the varying size of the cycle. So on the first row, we want to collapse just one vertex. On the second, we want to collapse two vertex. Eventually, that would become a triangle. And the third row, we are going to collapse three vertex, which is eventually going to be a larger triangle. And in order to collapse it, there are two terminologies that are really important. One is called the hub graph. So what it means by hub plus one is that it essentially collapses the hub vertex, which is the center vertex, plus one rim vertex. So hub plus one means that you collapse one vertex plus the hub vertex. Now, same goes by hub plus two and hub plus three. Now, hub terminology also leads to MK. So MK, K is the number of vertex on the rim that are not collapsed, that remain uncollapsed. So in the first row, there's only one outer vertex being collapsed, which means that there are 3 outer vertices that are left uncollapsed. So it renders an M3 graph. Now at this point, it is really useful if you bring up the idea of Laplacian matrix, because what if we can draw some Laplacian matrix on the collapsed MK graph? So for M1, we can say that M1, the Laplacian matrix, is on the right side. But see how I delete the first row and the first column, and all we left that is important for us to care about is the one that is remain undeleted. But if we compute the determinant of that, it will give us the number of spanning trees in this graph. Now, this is the second part of Kirchhoff's theorem, is basically that you delete the first row and the first column of the Laplacian matrix of an MK graph, and you compute the determinant of that. The result will give you the number of spanning trees in this collapsed graph. Now, same will go to 2. The M2 graph has a Laplacian matrix that are 3 by 3, but we still delete the first row and the first column. It renders a remaining of 2 by 2 Laplacian matrix, and the determinant of that will give us the number of spanning trees. It can be also understood in a way that since you have M2, the only thing that we are interested in is to compute the determinant of that 2 by 2 Laplacian matrix. Or the same will go to M3. We are only interested in computing the 3 by 3 matrix. Well, if it goes to MK plus 1, so the same thing, the number of spanning trees in this MK graph is just the determinant of this K by K Laplacian matrix. One interesting observation, though, is that we can use the idea of Fibonacci nut numbers. So take a look at this. The determinant of M1 is equals to 3. Determinant of M2 equals to 8. Determinant of M3 equals to 21. But all of those numbers are actually Fibonacci numbers. In fact, 3 is the fourth Fibonacci number, 8 is f of 6, and 21 is f of 8. Now, there is a very wild guess, and this guess is that since, okay, let's start by base step. Since M1 equals to 3, and it is the Fibonacci number of 4, what I can guess is that M of k equals to f of 2k plus 2. Now, this applies to this base step, but the actual proof or the actual idea behind this will be discussed in the next few minutes. So this might seem counterintuitive in the first hand, but it is going to be helpful as we carry the discussion forward. So just another way to approach this. Let's just say that there's a graph of mk, and let's assume that this k is equals to 5. So we're going to compute the determinant of m5. It is essentially the result of 3 times the determinant of m4 minus 1 times the determinant of m3 plus 0. Now, why is it 3 and why is it minus 1? Do you still remember how we compute the determinant of a 3 by 3 matrix? It is the idea that we start from the first row, we take out the first element in the first row, and then we use that to multiply the rest set of the matrix that is not affiliated with this number. This number is affiliated only with first row and first column, right? So the first number on the first row is 3. The second number is minus 1. So we take out minus 1. Now, what we do here is because we have collapse, right? So keep in mind that there's a collapse. We're going to collapse the second row and the second column. So essentially, it is going to be minus 1 times a 3 by 3 M3 graph. Now, you also have to plus, right? But the third element and the fourth element and the fifth and onwards, they are 0. And so 0 times anything will be 0. So to conclude, the determinant of m of k equals to 3 times the determinant of mk minus 1 plus, because it's a minus 1, so it's a plus the determinant of m of k minus 2.